In this lecture, we're going to be talking about trees of all different kinds, not the biological trees, the mathematical trees in the context of graph theory. So trees are special kinds of graphs. Let's go through the definitions and then see why we might care about trees. So first of all, definition of a tree. A tree is a connected graph with no cycles. So there's two properties that must hold for a graph to be a tree. First of all, it has to be connected, meaning I can get from one vertex to any other vertex via a trail or a path, or a walk, trail, or a path. And it has no cycles. So anything like this or of any other length in terms of a cycle is not allowed. So remember the property from the previous lecture on connectivity that if I do have a cycle, then I can cut out any edge without disconnecting the graph. So in that sense, trees are quite efficient structures because they have no cycles already. So they already have no redundant edges that add nothing but alternate paths for the connectivity of the graph. Of course, every tree has leaves. A leaf of a tree is a vertex of degree 1. So for example, if I have a tree that looks like this, it's connected and it's got no cycles, these vertices are called leaves. If you have more than one tree, you are going to get yourself a forest. And that is exactly what it sounds like. It is a collection of trees. It is a bunch of different trees put together but not connected. So it's a cycle-free, disconnected graph. Let's draw a few examples of trees. So first of all, to justify why they're called trees, you notice that you can draw them sort of from the root up. And as long as what I draw is connected and has no cycles, I do have myself a tree. There we go. So if I were to add, for example, this edge, it will no longer be a tree. And again, this is what motivates the actual name is if in a tree with branches, you don't have one branch going back into another branch. The branches are all disconnected, but you can get from, let's say, any leaf or any branch all the way down to any other vertex in the tree. Everything in the tree is interconnected. Now, of course, you don't have to draw tree graphs to look like trees. They can be drawn any other way as long as they're connected. My iPad thinks that if I'm drawing in a straight line, it should be a true straight line. So this is a tree graph. It is connected and has no cycles. Now, of course, I can actually add more things to this graph without making it, without ruining the tree property. For example, it could be something like this. It's connected. It has no cycles, so this is still a tree. And what I have now is, if I think of the graph that is the union of all of these graphs together, then this will be a forest. We can go through and notice what some of the leaves in these graphs are, right? So for example, degree 1 vertices here are the leaves, all of these. So the leaves are kind of like your boundary vertices, the ones that are not extending the graph any further. The leaves here are going to be the endpoints, and the leaves here are going to be everything hanging off of this little caterpillar looking thing. One interesting result about trees is the following. Any tree with more than one vertex has at least one leaf. Again, because they're sort of boundary cases, they form the boundary after which the graph is no longer extended into other vertices, and therefore they have to have at least one boundary. Now, you are talking about trees with more than one vertex. So the moment I have myself two vertices, in order to be a tree, it has to be connected. You will have at least one leaf. So this one has two leaves. If I were to add more vertices, this is the smallest possible tree on 3 vertices, and it has 2 leaves, and so on and so forth. I'm not going to go through the rigorous proof of this property. I think it's pretty intuitive and believable. The actual first theorem that has to do with trees describes 3 different ways to really define a tree. So the way we defined it was it is continuous and it has no cycles. Now here we have 3 equivalent definitions of that. T is a tree. T is connected and has n-1 edges. there's a unique path between any two vertices in a tree. So the key word here in the last portion is unique. And this kind of what makes trees so efficient. There are no more than one path from one vertex to the next. In a tree, if I have a vertex and I want to connect it to another vertex, there is guaranteed to be a path because the tree is connected, and it's going to be unique. So it's going to be the only way to get from there to here. Now, if you are to prove that statements are equivalent, what you need to prove is that A implies B, B implies C, for example, and C implies back in. So you're kind of actually constructing another tree in between these statements, the connected tree. You can get from any one of these subparts to any other. I'm not going to go through all of the proofs. I am only going to prove the fact that the first property, it's called A, implies the second property, that's called B. So I'm going to prove that if T is a tree, then it is in fact a connected graph with n minus 1 edges. And the way I'm going to do it is what you first will consider to be unexpected. There we go. We are going to prove it by induction. In fact, induction is very useful for a lot of graph theoretical properties. Remember that induction is essentially reducing the size of something by 1 and then proving somehow that the property will hold in perpetuity. Induction is a very structural proof. So we're first going to start off with the basis step. Now here, the basis step is the smallest tree for which this will hold. So what about the tree with one vertex? Well, if a tree has one vertex, then this is my entire tree. How many edges does it have? Well, it has 0 edges because it's a simple graph, so I'm not allowed loops or anything like that. And this being my n, so let's actually denote that. Let's say n equals 1, just to be more precise here. And we can see that it has n minus 1 or 0 edges. So this property, it's connected. Well, one vertex is connected to itself and it has n minus 1 edges. We are good to go with our basis step. Let's write down our inductive hypothesis in full so we're able to refer to it later. So what we're going to do is our inductive hypothesis is going to supposing that every tree on k vertices is both connected, well, it's a tree on k vertices, so it's connected, has k minus 1 edges. Okay? So notice, first of all, that this connected portion, I don't have to worry about. Just by the virtue of being tree, I already have that property. The only property that I have to concentrate on proving is the fact that my graph has n minus 1 edges. Okay, so then in the induction manner, what we're going to do is we're now going to consider a tree, so a connected graph, on k plus 1 vertices. What we need to prove, so let's write it down here, need to prove that it now has the number of vertices minus 1 edges. So what we need to prove is that it has k edges. Okay, good to keep in mind what our final step needs to be. Now, if I have a tree on k plus 1 vertices, I can first of all apply this theorem. Any tree with more than one vertex, well, my base case was 1, so my k plus 1 is at least 2. So any tree with more than one vertex has at least one leaf. So what I know about this tree is by above theorem, this new tree of mine on k plus 1 vertices has at least one leaf. We can say has a leaf. Okay, let's draw a picture just to really give ourselves an idea of what that looks like. If my leaf, let's call it V, is out here. So my leaf, remember, is a vertex of degree 1. So it can only have one edge coming out of it. This is my leaf. Let me label this leaf. The rest of the graph has to reside somewhere here, right? So my leaf is connected by one edge to all of the other, to one vertex somewhere in the rest of my graph. And this is where the induction kicks in. This is the rest of the graph. Remember that my tree altogether has k plus 1 vertices. I've now managed to separate one of them as being the leaf, which means that what I have here inside now has k vertices. And once I have k vertices, I can apply my induction hypothesis. Every tree on k vertices has k minus 1 edges. So, by induction hypothesis, this tree on k vertices has k minus 1 edges. So there are k minus 1 edges here, one edge here, k minus 1 plus 1 gives me the k edges that I actually need. So together with edge connecting my leaf, we have k edges. And this is all that we needed to prove. One thing to note here that I didn't speak implicitly to, but let's actually go through and check the details, is I assumed that what I have after cutting off one of the leaves is still a tree. Well, notice that removing the leaf does not ruin this from being the tree. A tree is a connected graph. I did not disconnect this graph because I did not remove any edges from within it. And a tree is a graph that has no cycles. Well, the entire graph was a tree and had no cycles. Removing an edge certainly doesn't introduce cycles either. So I can safely assume that what I have here is a tree. Let's now take a look at the overall structure of this proof. I started with, as the usual, induction, showing that the property that I want to prove holds for the base case, in this case 1. I then set out my induction hypothesis to assume that my desired property holds for some value of k, and then I looked at the instance of k plus 1. Utilizing something that I know about trees in general, I've managed to pull away one vertex and reduce my theorem to the tree on k vertices so that I am able to use the induction hypothesis. Isn't this a beautiful application of induction? Induction is a very powerful tool because it's a proof technique that holds across various areas of mathematics. And here is an exact perfect example to show how not only does it work for proving something about summation properties or division properties, it also works beautifully in graph theory. Moving on, we're going to talk about what are called rooted trees and then later on binary trees. So rooted tree is a tree in which one vertex is distinguished from the rest, and it's called the root. It doesn't matter what that vertex is, really. We're going to pick it depending on our particular needs. It's simply one vertex that we will consider to be the so-called root. The level of a vertex is then the number of edges along a unique path. We've just learned that in every tree, there's a unique path between any two vertices. So the level is the length of the unique path between that vertex and the root itself. The height of the tree is the maximum level of any vertex in the tree. Now, let's draw an example of a rooted tree and see how these apply. So what I have, for example, here's my root. I'm going to draw first with the root already shown as the root. Now, in graph theory, we actually draw trees down, not up. So like, if you look outside, your trees will look like they're looking up toward the sun, so they will be moving up. In math, we draw our roots down. I think it's actually basically for physical explanations, because if I start with my root on the bottom, I have no idea how much space to reserve for the tree because it's growing up and I might run out of the simple paper screen that way. If I start with a root, I know I have to grow it down. So if I need more space, I can just give myself a little bit more room. So we would start with the root on top. So for example, I can extend my tree out. Remember, tree, I need to keep it both connected and I need to keep it cycle free. So that means I cannot connect, let's say, these two vertices to each other. Okay, and let's say I have something maybe like this. I think that's pretty good. Let's throw in one more here. Why not? Let's extend it out into almost all of the white space that I have. Okay, so this vertex is the one that has been designated a root. Notice that I can redraw the exact same tree with a different root. So if I, for example, decided that this is my root, then I need to provide a picture where my tree goes from that, just to make it a little bit more clear. And then the rest of it really follows along this side, right? Because it's this that expands all the way out. Okay, but once it's been designated a root, I can talk about the level and the height. So levels, the root itself is at level 0. So this is level 0 of my tree. Then the number of edges along a unique path between it and the root, the number of edges between this vertex on the path to the root is just 1, this edge, and same for this vertex. So the level is beginning to make sense. If I draw the tree this way, then every edge that I am adding adds to the path between that vertex and the root, and therefore increases the level by 1. So these vertices are level 1, these vertices are level 2, these vertices are level 3, and so on, right? So this is level 3 vertices, and this is level 4 vertices. The height of the tree is the maximum level, which also, of course, makes sense. So my biggest level here is 4. The height of my tree is 4, which is also the length of the path from the root to the furthest, leaf. So for example, from this all the way down to one of those. Next up are the definitions of relationship between the vertices, not just with respect to the root, but with respect to each other. The children of a vertex V are all vertices adjacent to V that are one level further away from the root than V. So if my vertex V, for example, is, let's say this one. Okay, so let's say this is my vertex V. The children of V are the ones that are adjacent to it that are further away from the root. So the children of it are going to be the ones that are lower down. Okay, so V here looks like it only has one child. Let's give it another one. Why not? Okay, so all of these are going to be children of V, but notice that so it has to be one level further away. So this is no longer a child of V. It's, if you want to carry on the analogy, is going to be a child of a child of V. If W is a child of V, then V is called its parent. Okay, so we really can think of these as in the family relations. So if this is my V, then its parent is one level up. Okay, so this vertex is a parent of V. And distinct vertices that are both children of the same parent are called siblings. Okay, so where can we find two vertices of the same parent? Well, not so much along this path, but for example, there is more than one vertex here. Or for example, V has siblings too. So all of these are going to be siblings. So these are siblings. And there is other options, of course, here as well. These are siblings, and so on. This kind of language simply allows us to talk about the relationship between the vertices that are within the tree and not necessarily the root itself. So next up here we have an example with a particular tree with the root designated at vertex W, and a bunch of exercises for you to go through and make sure that you understand how to use the words. Take a minute, pause the video. Me going through this example is not going to be nearly as helpful as you going through this example, so fill this out by yourself. One thing I'd like to point out is, let's take a look at part D. I'm actually not going to do it because I do want to encourage you to familiarize yourself with the terminology, and this is very straightforward. But one thing I want to point out is the parent relationship. So for example, the vertex W9 here, right here, notice that in terms of parents in the trees, every vertex only has one parent. A vertex cannot have two parents going up this way, right? Because notice that if it did, this parent also has to be connected to the root, and we would have had to create a cycle in order to do that. So parenthood is a one person or one vertex only relationship, right? Every vertex only has exactly one parent. Now, another type of rooted tree is what we call a binary tree. And that is a concept that is present in a lot of computer science applications. It is a rooted tree where every parent has at most two children. Okay, so binary meaning two. So every single vertex within has at most two edges going down away from the root. Now it says at most two, so I could have vertices that only have one child. Each child in a binary tree is then either called a left or a right child. And normally that's how we actually label them. We go through and label left children, and it's in a different way than right children. The left subtree of V is a binary tree whose root is the left child of V. And similarly, we can define the right subtree. So let's see. Here, this is my root. Okay, so let's label this tree with the terminology that we just came up with. So this is a root. If I have these two children, U1 and U2, my U1 is the left child of U0, and my U2 is the right child of U0. This also leads me to notice that, for example, U1 has left and right child, but U2 only has one child. There's no left children the way it's drawn, it only has the right one, okay? So let's note here that U2 has no left child. Okay, I can't say left children because it's a binary tree, so it has at most two, one left, one right, so it has no left child. But thinking about U1 here, I can note that in terms of subtrees, this is a left subtree of my U1, okay, and it has U3 as a root, and this is a right subtree of U1. Now, the lack of left children for U2 means there's no left subtree for U2, but there's of course still a right subtree for U2, okay? So a binary tree, at most two children per parent. A full binary tree is a tree where every parent has exactly two children. So most of the, all of the relationships are exactly present. And this is also leading us to actually be able to calculate things. So if tree is any binary tree of height h and t leaves, then we have the following relationship. T is at most 2 to power h. Or equivalently, when you write it in logarithmic and not exponentiation form, this is equivalent to this. Now, how do we actually see this property? Well, let's draw it out. Notice that it's 80 binary trees, so I can have at most two children, but the relationships are less than or equal to, so let me draw a full binary tree and then see how that actually works out. So every vertex has two children. Again, in the case of any binary tree, it will have exactly two children. So I'm drawing the most edges that I can have, knowing that some of them could be missing, okay? I'm not gonna draw anymore. This is already quite a few. And then notice that, of course, in terms of levels, this is level 0, and then I carry on with the levels as I move further away from the root. Now, how many vertices are going to be present on each level? So on my very top level, I have one vertex. On the next level, this vertex divides into 2. So now I have 2 vertices. On this next level, every vertex of the already present ones further divides into 2. So I have to multiply the number of vertices I already have by 2 because each one of them will have 2 children. Next up, I have 4 here. I have to multiply it by 2 because each vertex will have 2 children, and so on. So what I notice, of course, is I am forming powers of 2 as I go down. Or in fact, I'm forming at most powers of 2 as I go down, because I could have that some of these edges are absent. Of course, notice that that means that at any given level, I have at most 2 the power of the level number of vertices. Every time I went down one level, I added 1 to my power of 2 because every single vertex has divided into 2. So that means that on level h, which is the height of the tree, I will have at most 2 to power h vertices there. Now, at the level that is the height of the tree is the last level, which means that I'm not extending any further past here. And so those are the only vertices of degree 1. And those are, in fact, my only leaves. Since I've labeled t as the number of leaves, I get the expression that t is less than or equal than 2 to power h. Now, rewrite it in the logarithmic form is actually just applying exponentiation and logarithmic conversion rules to this formula that we've developed. Now, all of the things that we have talked about in terms of trees is going to help us determine whether or not trees, or generally graphs, with certain properties exist or not. This is not something that I can just show you how to do and you will learn from. This is something that you really must do for yourself. So pause the video and go through these. I will specifically not cover this material because I want to ensure that you're trying these out. These specific questions are from past exams in the course, so this is important for you to know how to get through. Okay, there's quite a few of them there. Next up, and the last part of this lecture, is we're going to talk about how to use binary trees for actually representing algebraic expressions. The way we do that is at the root of a little binary tree, like really the smallest possible binary tree, is going to be an operation. And then the children are going to be the numbers that we operate on, and the order here is important. The left child is going to be the first number that we apply the operation to, and the right child is going to be the one on the right, okay? So here we read as 5 plus 6. If I wanted 6 plus 5, I would have to build my tree in that order. So notice that the left and the right child are flipped. Now, of course, in the plus, it doesn't matter, but in the minus, it already does. 5 minus 6 is represented by this tree. 6 minus 5 would have to be if the children were swapped. For some operations, the property is called commutative, when the left and the right child order doesn't matter, but for others, it of course does. So let's say we would like to draw a binary tree that represents this expression, a divided by c plus d. This is where you have to think about the order of operations, which is why drawing these trees is important in terms of if you're programming this type of thing in. So order of operations suggests that I have to do what's in brackets first, and then apply the division. So if I have to do what's in brackets first, it's c plus d. So I'm going to have my little binary tree this way, c plus d in the proper order. And then I have to have a divides all of this. So I have to have my divide vertex, whose left child is the node a, and whose right child is c plus d. Okay, fairly straightforward, but the order of operation really matters, right? So if you constructed something like a divides c and then plus d, it would be a very different kind of expression. Now, let's go a little bit more backwards. We have a tree, and we're now asked, what expression does this represent? So the root operation, being the plus, connects the left subtree and the right subtree. The right subtree is only one operation, so fairly easy to write out. The left one is still quite a bit of a handful, so we have to go down each level and think about what operations those include. Take a minute, try to see if you can come up with this expression for yourself. So I'm going to start at the plus. So my plus operation connects the left subtree with the right subtree. I can fill in the right subtree here because it's fairly straightforward. So I'm going to add a division of d over e. So d over e is being added, this is my d over e, to this right subtree. Okay, now for the right subtree, maybe in this case, I'm going to work bottom up. So I have a minus b as my beginning, a minus b. This is what this subtree represents. And then what I have here, the whole thing, so I can insert the brackets, is being multiplied by c. And then once I have that, that represents my entire left tree, this has to be added to my right tree. So I can move this expression up here. And there we go. Now, using this, I'm going to leave the other two questions to you. Be careful about how you actually operate on the order of operations and the tree. Trees are some of the trees that have been extensively studied. So not only do we have many different theorems that quantify and qualify various properties of trees, we also have a number of different algorithms that help us either traverse the entire tree or search for something specific inside a tree. And here, this picture represents just a few different ways to do so. So for example, depth first search is exactly what it sounds like. You're going to start off and go sort of as low as possible at first before backtracking all the way up. And again, following each subtree to its entire height first before coming back up. There is the also things like breadth first search, which searches in a sense by level. Okay, so decides to expand horizontally rather than vertically. And there's a number of ways to order nodes within the tree. So pre-order, in order, post-order. Trees are extremely useful structures, and I hope that seeing the mathematical connection to them will help you understand them better in computer science when you come across them.